Hello everybody, welcome to this Henstitute help session. In this one, I'm going to go through the concept questions for the friction Atwood's machine questions and problems. We covered number 1 in class, but I thought it'd be good to kind of cover it again. And then some classes got to see 2, 3, and 4, some didn't, so I thought I would just kind of take a look at them, and I'll catch 5 and 6 in a different one because they deal with Atwood's machine as opposed to friction. So in number 1, really the kind of the main idea, if I look at some object sitting on a surface and I do a free body diagram, we know we've got the force of gravity pulling down on it. We have some kind of normal force pushing up on it. And if nothing else is pushing up and down, those just equal each other. And then you come along, and in this particular case, we're going to apply 30 newtons of force. So we're going to pull on it with 30 newtons. That would be some kind of FP, a pull force, applied force, FA, whatever. And then we're going to have friction. Okay. Now, the hard question on this one is they want the magnitude of the friction force. Well, the problem is I don't know what this friction force is going to be until I determine whether the object is going to move or not. So what I'm going to do is I'm actually going to borrow this 10 kilograms and figure out how much this object weighs. So it'd be 10 times 9.8, or in other words, 98 newtons. Hence the reason why you can see D on there. So that's really not going to be the correct answer. That would just be the weight of it. Since it's just sitting on a flat surface and we're only pulling horizontally, the normal force up here would also equal 98 newtons. So my suggestion on this one is let's calculate the maximum static friction using this coefficient. So I'm going to go to this lovely equation and say the maximum static, which is the fun equation. We're going to calculate it. So we're going to take 0.36 times 98, and this gives us 35.3 newtons. So a lot of people see that and they instantly jump that, aha, there's my answer, and they say it's answer C and they're done. But that's the maximum static friction that can apply on this. If I look back at my problem, I only have 30 newtons actually applying on this. So if you remember, friction is really a Newton's third law reaction type of idea. So if I pull with 1 Newton, friction only has to pull back with 1 Newton to keep it from moving. Now, if I pull with 1 Newton and it actually starts sliding, it's a different situation. But if I pull with some force and it doesn't actually move, then I can see that that's how much friction has to pull back with. Since 35.3 is larger than 30, it tells me that this applied force is going to equal my friction force, so that this box is not going to move. So this is not moving. And hence our correct answer is B. Now, why would this one be over here? Well, if I use 0.15, we actually would find that the kinetic friction comes out to be that 14.7 newtons. It would be the 0.15 times 98. And so the question is, when would that pop in? That's smaller than 30. Shouldn't it actually be kinetic friction? Well, in this particular problem, if they had pulled with enough to overcome the maximum friction, then yes, you are correct. So if they had pulled with, say, 40 newtons up here instead, then that would have been larger than this, and therefore they would actually have kinetic. So really, it's only 2 options would be either A or B, or potentially C if you pulled with exactly static, and then definitely not D. Okay, so that's a little bit of help. Next up, 2 and 3. They're both dealing with friction, but the difference here is number 2 asks about the coefficient of friction, and number 3 asks about the force of friction. So the force of friction, our fun equation, is the coefficient of friction times the normal force. So this is our fun equation. We can see fun diagonally across there. So really I have to answer 2 before I can answer 3. The key idea is that the coefficient of friction is really a measurement of how smooth a surface is. Measurement of smoothness or roughness. Roughness. So the larger it is, rougher. the smaller it is, the smoother it is. So if I have identical lab tables and I take them to different places, do they suddenly become rougher or smoother if you don't actually change anything about them? If I don't change anything about them, they are the same roughness. They're the same smoothness, whichever way you want to kind of think of it. So really, in number 2, it doesn't actually matter what the acceleration of gravity is. All of them are just going to have that same coefficient. Now in 3, what about the force of friction? Well, if I look at my equation here, my fun equation, that's great. Here's another way to kind of look at it, to relate it with gravity. In this particular example, number 1, our normal force was just equal to the weight. So we have already done this before. I can actually replace this with m times g, and we came up with the gum equation. So friction can be found on a level surface where nothing else is pushing up or down on it with gum. So it'd be gravity times the coefficient of friction times your mass. So now what we see is that gravity and friction are directly related. So the higher the gravity, the more friction force there would be. It doesn't actually affect coefficient of friction. It's actually a direct relationship between those. So if I'm looking for the greatest force of friction, I have to start comparing their accelerations of gravity. And you should be able to figure it out from there. The only thing to watch out for is this says A is Earth and this says B, Earth. This is supposed to be an A. So you're going to be highlighting your answer anyway, so if you highlight that, you should be fine. So don't worry about the letter. The last one, number 4, is talking about ranking the kinetic friction force. So again, I'm going to kind of borrow this equation that it's coefficient of friction times the normal force. And you go, okay, they're identical surfaces, identical blocks. So therefore, the coefficients are the same. Shouldn't that mean the friction force is the same? Well, do we change anything about the normal force? So if I start looking at this particular problem, in A, they pull horizontally. So all we have is we're going to have friction acting in the opposite direction. And they're pulled across a horizontal surface as shown in the drawing. It doesn't actually say whether they're accelerating or not, but our kinetic friction would pop in like that. So let's assume it moves at constant speed. These two would just equal each other. The key idea is now when you pull diagonally like this force is actually doing 2 things to this box. It is actually, I'm going to switch out colors, it's actually lifting up on the box a little bit and it's pulling it forward. So friction comes along and friction is going to act in this direction. So if it moved at constant speed, this horizontal force would be a little bit smaller and therefore kinetic friction would be a little bit smaller. So that's one way to think of it. But here's another way to think of it. We know we have the force of gravity pulling down on it, and all these boxes are exactly the same. So all of their force of gravity should be the same, but we have a normal force. In this case, the normal force has to equal that force of gravity so that it doesn't move up or down. But in this case, it already has a little bit of a purple force to help it out. So it doesn't actually have to apply as much force. So the blue and purple here can balance out the force of gravity. Since the normal force is smaller, if this is a little bit smaller, then friction is going to be a little bit smaller. In C, the diagonal force does a different situation since it's acting diagonally like this. Then it's pushing down on the box with a certain amount of force and pushing forward on the box. And then friction is going to oppose that. I know this is kind of messy. But this downward force actually causes the fact that the normal force has to balance this and this. So the normal force here would be larger to try to do that. So it's kind of actually ranking the 3 normal forces. And the larger normal force would be the larger friction force and vice versa. So if we're going from smallest to largest, we actually want the smallest normal force, which would be B, then next A, and then finally C. So you can kind of see it by just ranking those to actually get it. Hope that helps.